Providing cooling in enclosed spaces can require a large amount of energy. Therefore, cooling the air without making use of a refrigerating machine should be exploited. To reach this goal, some natural technical solutions are available which were sometimes adopted in the past. Natural air cooling systems are usually subdivided into two categories. The first includes those based on the adiabatic humidification process. The second one considers a solution exploiting the low temperature of the subsoil, which is lower than air temperature in cold and temperature climates in summer. The latter is not suitable for hot, humid climates because the temperature of the subsoil up to a depth of 3–4 meters is very close to the air temperature. In hot, arid climates, where the outdoor air temperature during daytime is higher than that of the subsoil, the system would only be effective for 1–2 weeks, which is the time taken from the soil around the buried pipes to warm up. Alternatively, the evaporative cooling principle can be exploited, where the underground soil is cooled by keeping it wet. The evaporation cools down the soil and the gravel or pebble layer protects it from the solar radiation. In hot arid climates, the adiabatic humidification process, or evaporative cooling, is always effective. Spraying water into a stream of air cools and humidifies it. In very hot, dry climates, this physical phenomenon can be used to improve environmental comfort. One way to take advantage of this physical principle and at the same time to facilitate a good ventilation is to cool the air by adiabatic humidification sinks in a tower and spread it into the space. For a first approximation in sizing a downdraft evaporative cooling tower, a 5-step procedure can be followed. First, from climatic data of the location, find the design dry bulb temperature and the coincident relative humidity for the site. Such data represent the worst climatic condition to take into account when sizing a cooling system. Second, on the psychrometric chart, mark the points corresponding to the chosen design values. For instance, dry bulb temperature equals 35 Celsius degrees and the relative humidity equals 20%. Third, move along the line at a constant enthalpy until the relative humidity curve 60% is reached, to take into account the fact that not all the airflow will be involved in the evaporative cooling process, that is, the effectiveness of the sprayed pad system. Fourth, find the dry bulb temperature after the adiabatic humidification. The value found in the example is 24.5 Celsius degrees. Fifth, calculate the airflow rate using the equation related to the stack effect. In this example, Ti is assumed equal to 32 Celsius degrees as a first approximation. Mind that indoor temperature should be calculated iteratively using the room heat balance. H is equal to the distance between the center of the pad and the center of the outlet, and A is the net openings area. The procedure assumes that the walls of the tower are insulated. If this is not the case, the cooling capacity will be less than that calculated. If there is wind and the inlet is properly designed, the cooling tower also acts as a wind catcher and the airflow is enhanced. For optimal operation, the outlet openings should have a total area not less than that of the cross-section of the tower, which in turn should be about half of the total area of the inlet openings. There are several examples of cooling towers in modern buildings, such as the Zion National Park Visitor Center in Utah, USA, and the Council House 2 in Melbourne. In the first one, all cooling loads were met with natural ventilation using computer-controlled clerestory windows, evaporative cooling from the cooling towers, and the careful design of the shading device and daylighting apertures to minimize solar gains. The only mechanical input to the cooling system is a pump to circulate water through the evaporative media. In the second one, the showers along the southern facade of the building cool air for intake and uses it in the ground floor. The showers are made from tubes of light-white fabric 1.4 meters in diameter. As the water falls within the tower, it sucks in air from above. This air falls down the tower and it is cooled by evaporation from the shower of water. The cool air is supplied to the retail spaces and the cool water precools the water coming from the chilled ceiling panels. In climates where the direct evaporation of water in an airstream would lead to a too high relative humidity, an indirect evaporative cooling can be used. With this technique, the air cooled and humidified by the process of adiabatic humidification is sent to a heat exchanger, which the ambient air to be cooled passes through. The air processed by the heat exchanger can come from outdoors in case of open circuit systems, or directly from the ambient if a closed circuit system is provided. In an urban environment, it is very often not possible to keep the windows open for natural ventilation. Consequently, even in those periods when the outside air temperature is such that, with adequate ventilation, the air conditioning should not be needed, it becomes necessary to use it. In these cases, or in spaces with no air conditioning and where air movement is not sufficient, a ceiling fan can be used. It is also useful when used in conjunction with air conditioning, because the increase in air velocity means that the air temperature can be increased with the same comfort level but lower energy consumption. The simultaneous use of fans and air conditioning allows the temperature of the thermostat to be raised to 28 Celsius degrees instead of the usual 26, allowing an energy saving in order of 15 to 20% with the same comfort level. Ceiling fans are also very effective when natural ventilation is not available because of lack of wind or a weak stack effect. For this reason, they should be combined with natural ventilation strategies for best results. Some tables can be used to size ceiling fans considering the length of the room or its floor area. In hot arid climates, the effect of a fan can be improved by exploiting the evaporative cooling effect with the use of a misting fan. It is a normal fan equipped with fog nozzles, which is designed to produce a very fine mist so that the water evaporates quickly. It combines evaporative cooling and convective cooling, at the same time reducing the temperature and increasing the velocity of the air. The improvement in the level of comfort can be significant. Misting fans are also appropriate outdoors. As seen in this lecture, energy needed for cooling can be saved, avoiding or reducing the use of mechanical systems. In fact, these one can be replaced or integrated by some passive systems or low-energy devices.